Okay, so in this video we're going to be looking at width and using confidence intervals to test claims. So the testing of claims for confidence intervals, I'm just going to say, will be put over two videos. In this video, because we're also looking at width and we're introducing that as a new concept, we'll focus on actually testing claims for confidence intervals in the next video, which should be the final video on confidence intervals, which also focuses on confidence intervals that aren't 95%. But in this one we'll be looking at width and the basis behind testing claims, like the general idea and actually looking at the general process that we use if we don't want to use hypothesis testing and we have a sample mean available. Okay, so what we want to look at here is a 95% confidence interval. And as you can see on the board, we're using the value that I discussed in the last video, 1.96. And the width is essentially from the lower point. So if I were to draw a distribution up here, it's from the lower limit, negative 1.96 as a z-score, to the upper limit with a z-score of 1.96. As we know, that holds 95% of our data. That is 95% of what is under the curve there. So the width of a confidence interval is going to be essentially from that point to that point. And you may remember at the end of the last video I showed you how you can use 1.96 sigma over root n equals a certain value to actually get the ideal discrepancy that you want with I believe we looked at if memory proves to be correct, which it may not, but I think we looked at drink bottles or soda bottles, and we wanted that 1 millimeter difference between the sample mean and population mean. We can do that in a similar sort of way here as well. But when we're looking at width, again, we're looking at lower and upper limit. That's the main thing to consider, and we're also looking at this formula here. Now I'll talk a little bit about how I derived this. So we've got 2 times 1.96 sigma over root n. Essentially 1.96 sigma over root n is the width of this, because it is essentially 1.96 sample standard deviations to the left of the mean. And it's the same here, it's 1.96 sigma on root n. That's the width of it. It's 1.96 lots of the sample standard deviation, because again we're looking at the sample mean. So again you may know that to be the sampling error. But essentially it's talking about a distance, how wide something is. And there's two of them. There's one to the left and one to the right. So that's how I get what the width is. That should be reasonably straightforward. You should be able to understand that now based on the z-score conceptual stuff we went over, what a z-score is, what a standard deviation is. So now what I've done is I've gone ahead and thought, well hang on, I can rearrange this for a value of n, and that value of n can help me get the desired width that I want. And the desired width is of course going to be quite important, because again it tells us how many samples we have to take to get a certain degree of precision. That helps statisticians, because there's no point surveying 1,000 people when to get the accuracy you want you only need 300 people. Again, getting that level of accuracy is very important, and we don't want to spend more money than necessary. So in order to rearrange it, I bring up square root n from the left-hand side denominator to right-hand side denominator, sorry, to the left-hand side numerator, and we get square root of n is equal to 2 times 1.96 sigma over w. Again, essentially I've done a swap. The w actually goes from the left-hand side numerator to the right-hand side denominator, so it swaps with square root n in that degree. Then, in order to get rid of that square root, I actually square both sides. So this is technically square root n squared, but you know that the square root and the squared symbol cancel out. So we end up with n equals 2 times 1.96 sigma over w squared. And that gives us the number of samples we need to take in order to get a desired width that we want. And again, this confidence interval, I cannot stress this enough, is the range in which the true population mean lies 95% of the time, based on a sample mean that we've taken. I covered that in the last video. It may take a little bit to get your head around. It is quite a conceptual issue and some people struggle with it, so I recommend just maybe watching the last video if you didn't quite get that, because again, it's a very important part, because understanding confidence intervals is really helpful in you actually interpreting and analysing it statistically. So now let's have a look at a few questions based around this N formula, so we can actually help us work out the degree of precision that we want. So a question might say that we may need to be within we may need to have a width of 5 for our confidence interval. So a width of 5 means that we have 2.5 on this side and 2.5 on that side, that we're allowing for difference in the true population mean. And again, it asks us what that sample would be in order to get that width. So we have a range of 5 total, but 2.5 either side. And again, it's just a simple matter of actually plugging values into the equation from reading the question. So I'm going to read out the full question, and we're going to go through this on the board. And again, we're going to be using that N formula that I just showed you how to derive through that very brief derivation there. So I'm probably going to choose a nice new colour. We have N equals 2 times 1.96 sigma over W squared. And based on this question, it gives us some values. All it really needs to do is give us a value of sigma and a value for the width. So now it says population is known to have a standard deviation of 34. It's always good to write down your facts, so we know that sigma equals 34, and we want to have a width of 5, as I said before. So in order to calculate this, we simply go that N equals 2 times 1.96 lots of sigma 34 over, and then 5, and we square it. Now remember to use brackets. It's incredibly important because that whole expression there is raised to the power of 2, not just part of it. So again, we grab out a calculator and we go through the process in order to calculate it. So when you're typing that into a calculator, the best thing to do is have an open parenthesis first, and then use a fraction bar. Again, I've told you that trick before. You use the alpha function, then you press y equals, and then you press 2. So when you go through that and you're able to calculate it, you should end up with a value of N that is equal to 711. So we need to take, and I'll write this down here, 711 samples are necessary. Again, I've done a teeny bit of rounding there to the nearest sample. Now, a very important thing to remember and consider with this is that you're looking for a certain width. So when you're rounding, and say you may have a number like 61.6, in fact, no, I'll make it slightly more challenging, 61.4. If you had that value, your common instinct would say, oh, round to 61, you need 61 people. However, there is a small limitation to that. We want to make sure that our width is equal to 5, the minimum value that should be taken in order to get a width of 5. I know this is not the value that we got there, but I'm just using this simplified value just to prove a point. But we can't say 61 from there, because when you think about it, we need to have more than 61.4. So if we round it to 61, then our width is going to be greater than 5. So if we were to use this formula and get some value like that, we'd round up to 62. Again, that's what I've sort of done with the 711 there. I've used appropriate rounding. So don't necessarily use common rounding rules, but use the logic of going to the next whole number, not the whole number that's necessarily the closest one. And that does take a little while to understand conceptually as well. But think about it as, okay, the width would not be 5 there. It would be 5.001 maybe, or something like that, because of that extra 0.4 of a person that is needed in order to get the width to that precision. Hence, I need to round up. Again, it's confusing. It'll boggle you a little bit. But again, if you just keep thinking about it, you just keep practicing it, and you get a really good conceptual understanding of, oh, I understand why, then you'll be fine. It'll be okay. So now it asks us what happens when we do it over 1. And when we do it over 1, we do get a slightly different answer. So when the width is over 1, again, we simply don't change any value except for that 1 on the bottom there. We go through a process, we type it into our calculator like we did before. A neat little trick in order to do things quicker is to just go up to that previous function and using the arrow keys, up button, and then press enter, and then just change the value of 1 by using the arrow keys to navigate. But when we look for an appropriate value of n, we should get 17,800 with a width of 1. So 17,800. And as you can see here, if we want that narrower width, we want that greater precision. So if the width is 1, then we know it's 0.05 either side. Then we see that we've got to take a much larger sample. We haven't necessarily, decreased the width by that much. It was 0.25, it was 2.5 either side before for the width. Now it's 0.5 either side. So yes, there is difference there. But as you can see, the number of people we need has just gone through the roof. And that's why statisticians generally say close enough is good enough. Because, of course, interviewing that many people compared to 700 just to get that small bump in precision isn't necessarily cheap, or it's not necessarily the quickest way of doing it. So again, people generally settle with, okay, what's an appropriate width? Let's just sample that amount of people so we get a good idea of what's happening, not necessarily the 100% accurate idea. And that's why stats is sort of like science. It's not as precise as other forms of mathematics, but it's still very, very fun and very, very interesting. So something I probably, you can follow along with if you want, but actually changing the width to 0.1 just to prove that last point. If we do plug that into our calculator, I won't go through the full instructions for it, but we just plug something like that in. You should get an even larger n value, because of course with 0.1 you're looking at 0.05 and 0.05 either side for the width, and you get quite a high value of people you'd need to survey, or how many soft drinks you'd need to take off the machine, or however many samples you need to take of whatever a sample is in context, but it's 1,780,000 when rounded appropriately to the correct number of significant figures, based on what the question generally asks in mathematics. We generally look at free SF, and also, of course, taking into account the width and how we have to say, well, okay, we can't round down, we have to round up. So that's a little look at width there, and it's a very interesting concept. Again, we did a similar thing with the end of the last video where we had to calculate n as the number of samples we needed to achieve a certain goal. This is another way of doing it. Sometimes questions will be worded differently depending on what they want from you. So be aware of the width and the other method. I would say the width method that we covered is generally more common, using this formula here. Again, you may not necessarily have to rearrange it. You could just go straight from the n one there and just base all your work around that. It's up to you, but again, if you know the derivation that I proved earlier in this video, then it just makes things a whole lot easier. So now, just to finish up this video, my second video on confidence intervals, I'm going to look at claims, and claims with confidence intervals. So again, we're going to be looking at drinks. Another nice, interesting question. Again, interesting idea of something that may possibly be normally distributed. But with this, we're actually looking at a 95% confidence interval in order to state whether it's likely that the population mean and the sample mean, well, what should I say, is it likely that the population means a certain value based on our sample mean, and working out the range of the population mean, which is what a confidence interval is. Sorry if that got a little confusing there, but again, terminology. So suppose a volume, which is given by V, of cool drinks dispersed into cartons by a machine is normally distributed with mean mu. And it can be adjusted. So we got that there will be a mean mu. The standard deviation will be fixed to 10 millilitres. It's always good that we have standard deviation that's fixed. The value of mu is supposed to be 1,005 millilitres. So, it's dispersing a reasonable amount of liquid. It's probably a good drink bottle and a bit full there. But the machine operator notices that the mu is actually 995. The operator therefore adjusts the volume dispensed by the machine. A quality controller tests 25 cartons and finds that their mean volume is 1,007 millilitres. Construct a 95 confidence interval for the volume mu dispensed by the machine. So we would be looking at the confidence interval based around the 1,007 millilitres, which is the value of mu. So in order to do this, we would simply go and say that the mean value in the confidence interval, we have 1,007, take 10 over root 25 times 1.96. And again, all I've really done is swapped it around. Less than mu, less than, and it would be 1,007 take 10 over, in fact that'd be plus 10 over square root 25 times by 1.96. And when we work that out with our calculator, again it says that we're working it out for the mu based on what they found tested, or the claimed population mean that he made, the actual claim of mu, or I'll just write underneath claim there, because we've got quite a few mu's. The one that he actually tested the machine to, what it's originally meant to be, and yes, all of that. But now we should get that the actual value there is 1,003 less than, and we've got mu as our test statistic, less than, and 1,011. And again, this is all in millilitres. So again, we can see that there's 4 millilitre variance either side. Again, you can calculate this either using the method I outlined in the last video for technology, or by plugging it into your calculator. But again, we're testing the mu claim, the actual 1,007 millilitres there. Since 990... okay, so let me read the actual question out rather than the answer. Use a 95% confidence interval to assess the claim that the volume dispensed by the machine has increased. So as we can see here, since 995 is less than the value of 1,003, which is the confidence interval for that claim based on the sample, we can say in confidence at the 95% level that the population mean has increased. So they've actually changed the machine to increase the population mean. So can we conclude that the volume of mu is now larger than 1,005 millilitres? And that's an interesting question. So we've got this claim that's 1,007 millilitres, but can we claim that's greater than 1,005? Well, the answer is, although that the sample statistic, or the claim given based on the actual sample that was taken there for the claimed population mean, was actually greater than 1,005, because of course it's 1,007. The smallest number in the 95% confidence interval is 1,003 millilitres, which is less than 1,005. This means that mu could be as small as this value when we're looking at 95% confidence, so a very, very good likelihood that that is correct. Again, it could even potentially be less, but at the 95% confidence interval we get a pretty good idea of what's happening, and it's very unlikely for it to be below that. But no, we cannot actually conclude that the volume of mu, based on the claim, based on the sampling that happened of 1,007, is actually that the actual mu is greater than 1005 now. So there's not enough evidence to support that claim in the end. So again, essentially it's very similar to hypothesis testing. In this case, the last question in particular would be that we have a null hypothesis of mu equaling 1005 and an alternate hypothesis of mu not equaling 1005. So again, it's something that really